So the next speaker is Raphaëlle Haywood, and she's going to tell us about identifying the spectroscopic signatures of magnetic fields.
I don't know how to use Adobe.
Yeah, I think try going back to the talk and double clicking on it again. It didn't.
Well, it's open here, but now how do I do full screen?
Oh, there you go.
All right, okay, great. Thank you, John. Good morning, everyone. I'm Raphaëlle Haywood. I'm a Sagan Fellow currently at the CFA, and I work on radial velocities of the sun and sun-like stars. And today, I'm going to talk mostly about the sun, but it is applicable to sun-like stars. The idea is that we want to understand what drives radial velocity variations in the sun and ultimately find proxies to identify these variations in other stars like the sun. And so in recent years, we've established that the suppression of convective blue shift via active regions is the dominant source of radial velocity variations. And today, I'm going to address two questions. What are the main, what features on the solar surface drive the suppression of convective blue shift? And second, can we get a good proxy for radial velocity variations so that we can then apply it to other stars? Right, so the suppression of convective blue shift, as Matt and Heather were saying this morning, in sun-like stars, you have convection going on, and the surface signature of convection is granulation. And so you have these large, bright granules that are emitting blue shifted light because they're rising up, coming towards us, right? And as the flow cools down on the surface, the flow then sinks back in the intergranular lanes, and so you've got red shifted light. But overall, you see more convective blue shift because you have the brighter granules, and they're also larger in area, so they contribute more to the spectrum. So overall, we have a net convective blue shift. And on the sun, it's about 200 meters a second, which it varies. So Heather was talking about the centimeter per second flicker. And that's not what I'm talking about. I'm talking about when you have a magnetic element, so magnetic regions on the surface of the star, they inhibit the convection processes. And so they're suppressing some of the convective blue shift. And that has an impact in the radial velocities of several meters per second. And that's the case for the sun when it's in its quiet phase, as I'm going to show you in a couple of plots' time. And so in recent years, work that I did in my PhD and also that Nadège Monnier and collaborators have worked on, we've identified that the dominant source of convective blue shift, of suppression of convective blue shift, it comes from the bright elements, so the faculae and the plage all over the solar surface, as opposed to the dark magnetic elements. So sunspots in the sun, and we've found in other sun-like stars like Coral 7, like other stars, we see that the radial velocity variations are not dominated by sunspots. They're dominated by the bright active regions. In the last few years, we've been observing the sun as a distant point-like star with no planets. We took out all the planets. And so we've now got 3 years' worth of radial velocity variations of the sun as it's entering its quieter phase. So this is quite recently. And here you see over 26,000 points on this plot because we're taking 5-minute exposures to average out the oscillations. The exposures are photon noise limited to just under 0.5 meter per second. We understand the stability, the long-term stability of the instrument. HARPS North is an exoplanet hunting spectrograph. So we need that precision and stability over long time scales. And so here we have the sun. And I will point out that you see, even though it's becoming less active, it's actually getting to its quietest point, you still see radial velocity variations of several meters per second to peak, and the RMS of this is about 1.5 meters per second. So that's significant when you're looking for another Earth, for example, in the sun, an Earth going around the sun, you're looking at 10 centimeters per second amplitude over a year timescale. So this is a significant source of noise for exoplanet surveys. But it's also a wonderful source of information for solar and stellar scientists. So what we did is that we reconstruct these radial velocity variations using high spatial resolution images from the Solar Dynamics Observatory. And in particular, the helioseismic and magnetic imager, HMI, on board SDO, has these images. So it tells you the radial velocity, the line of sight velocity at every pixel, which you can weigh by the continuum intensity. And you can take cuts in the magnetic field, so in the magnetograms, to then reconstruct your radial velocity variations. And I'm not going to go into any more detail about this technique, but you feel free to come and speak to me afterwards. I'm happy to talk about it. So we can reconstruct these radial velocities. And then these are, again, the Harps North radial velocities that I just showed you, except I've binned them in daily bins. Actually, this is work that Tim Milbourne has done, who's here today and going to talk more about this in a couple of days' time. So we have the Harps North radial velocities, and we overplot here the reconstruction using the SDO images that we've made. And so this is using the framework that I developed in my PhD, and we're including all of the magnetic regions. We're saying all of the magnetic elements are suppressing convective blue shift. And it works okay, but you do see a trend. And actually, we find that when we only include large, bright magnetic regions, then we're fitting much better. And we're actually getting down to the sub-meter per second level. So the residuals, if you subtract this model from the fit, from the data, you get about 80 centimeters per second residuals. So you're just above the granulation noise. But we've got rid of most of the rotation modulated signals. And so what we're finding actually makes sense, because the very small magnetic flux tubes on the surface of the sun are probably, they're still able to, they get pushed around by the granules. And so they don't suppress convective blue shift efficiently. Right, so if you want to find out more about this, go to Tim Milbourne's talk on Thursday in the Splinter session. Basically now, what I'm going to show you is we now see that we've compared the SDO-based model reconstruction with Harps North data of the sun as a star, and so we know it works fairly well. And I can now go and apply it to the entire SDO mission. So now you're looking at 7.5 years of reconstructed radial velocities of the sun, constructed in the same way as shown before. So just the large, bright magnetic area suppressing convective blue shift. And on top of it, what I can do is compute the magnetic flux. So SDO, the HMI instrument on board SDO, has the magnetograms. And so I can take each pixel, take the absolute value of the magnetic field, weigh it by the continuum intensity, and sum it all up and get the full disk, line of sight, absolute magnetic flux. And you can see that the two look very much alike. And in fact, we've got the magnetic flux versus radial velocities, and we get an excellent correlation. It works even better than the calcium H and K. So this is a beautiful time series of the sun observed as a star from the Mount Wilson Observatory, published by Ricky Egeland, and he's actually giving a talk just after the coffee break, so I'm looking forward to that. So when we take the magnetic flux and we do just a linear fit to the radial velocity variations that we reconstructed, this is what we get. And so just a linear fit just already gets us down. We reduce the RMS of the radial velocities by a factor of 2 almost, and we're down to 50 5 centimeters a second, which corresponds to what you expect from granulation with this kind of sampling. So, and actually I'll point out that you might see in the very active periods, it doesn't work as well. And what's happening here is that you're dominated by sunspots, which don't, they're strongly magnetic, but they're very small, so they don't, I guess they're not incorporated in the magnetic flux as much as the bright regions, the bright magnetic regions. But maybe we could combine this magnetic flux with, say, an FF prime type method, where you're using, for example, the flux to fit for this. All right, so I'll move on to my conclusions. We're observing the sun using the Harps-North spectrograph. We're looking at it as a star, as a point-like distant star with no planets. And we've got 3 years of data. It's a wonderful data set. We've confirmed using this data set that the dominant source of radial velocity variations is suppression of convective blue shift. And we now know that it's the large and bright magnetic regions that are suppressing this convective blue shift. And even when the sun is quiet, we still get about 1.5 meters per second of RMS in the radial velocities. So it's significant. And then finally, we reconstructed the radial velocity variations of the sun using the images of the Solar Dynamics Observatory and the HMI instrument on board SDO. We find that the magnetic flux correlates really well with the radial velocity variations. I will say that we can't measure the magnetic flux just yet for sun-like stars, slowly rotating stars. We do have, so the Zeeman Doppler imaging technique looks at much younger, faster rotating, more active stars, and it gets the large-scale magnetic flux, so not the smaller scale flux that we're looking at here. But there is another technique, the Zeeman broadening technique, where you go to the spectra and you look at the shapes of the lines, and the magnetically sensitive lines get broadened by the Zeeman effect. And Annelise Mortier in particular is currently working on that. She's developing a technique to account for the correlated noise in the spectra to try and extract the magnetic flux. And this would actually work better for the slow rotating sun-like stars. So hopefully we'll be able to observe it for other stars. Thank you.
Thanks, Raphaëlle. Questions? Mark.
So I was wondering if you took your HARPS spectra and you, say, censored the line list, that is divided up between magnetically sensitive lines and insensitive lines, and looked at the RV variations in each, where you have some Landé G factor where you say, well, this is sensitive and that's not.
Yeah, so actually Xavier Demusque is, I think he's giving a talk about this in the Thursday Splinter session in brightness variations. And also Chris Watson and Andrew Thompson are working on identifying lists of lines that are sensitive to activity and not sensitive. And they are able to get good results from that. I forget the specifics right now, but I would recommend going to that Splinter session.
Way in back.
That's Xavier.
Hi, Xavier Demusque here from the University of Geneva. I just want to comment on this point. So we were able to measure on HARPS, the Harps-North spectra of the sun, the velocity of each individual spectral lines, and this is what I will present on Thursday. And then we tried to look if lines with a strong Landé factor are more affected by activity, these kind of things. In fact, it seems that it's more complex than that. It's not just the Landé factor. There is plenty of other effects that are into this. But we were able to find spectral lines that are very sensitive to activity and some others that are not at all. So if you're interested about that, just come and see my talk on Thursday. Thank you.
And you've also, you've looked at the sun, but also Alpha Sun B.
one more question, I think.
So, Sasha Shapira, Max Planck Institute for Solar System Research. If I understood you right, you accounted for the inhibition of blue shift by magnetic field. But what about flows associated with magnetic features themselves? Yeah, because like if you have spots, we have huge horizontal evershed flows, and one would naively think that as soon as spot is close to the limb, you would probably see them in the data.
Yeah, very good point. That's something I want to look at in the future, actually. You do get those 50 to 100 meter per second flows going in or out of magnetic regions. That could be a factor.
Okay, let's thank the speaker again.